So today our topic is evolutionary computations using genetic algorithms. Context of this topic is to look at our options while creating expert systems when we are not uh, having access to human experts. How can we involve different machine learning algorithms to extract knowledge from data? We looked at artificial neural networks. And the second option we are going to learn today is genetic algorithms. We'll start with a little bit of background with the objectives in mind that we want to build a basic understanding of evolutionary computing and what are the genetic algorithms. We will start by discussing the basic fundamental laws of evolution and how do we map those into computational intelligence such that the basic core principles of evolution in biology can be mimicked in computational intelligence. The key vocabulary we are going to repeat again and again is going to be fitness function, evaluation and selection, reproduction, crossover, and mutation. Evolution, as we generally know, is the natural process of selection of best fit organisms. Over time, nature has a way to improve and adapt the organisms through natural selection. The process has multiple aspects to it, but it's called evolution in the quite popular theory in biology, how organisms evolved from single cell amoeba to complex intelligent species like us. So as natural selection leads to better and better solutions, we expect that somehow if we apply those same principles and operations in a search space for a population of solutions, we expect that we will end up with the best solution if we repeat the evolutionary process again and again. For that process, first thing that needs to be there in the first phase or step or condition is that there is a kind of heredity passed on from one generation to the other one. So in case of computational intelligence, that thing that we pass on to the next generation of solutions is the particular information encoded in terms of bits and bytes. Second, every time we pass information to the next generation, there is some variation. So next generation don't just get a copy of the earlier or parent generation, but there is a certain kind of variation, random or stochastic, at the same time a little bit of engineered variation that results in evolution. The third thing that should be there for evolution to occur is differential reproduction. So this concept says that some individuals in the population get a better chance to pass on their genes to the next generation compared to the other individuals. So one population will pass their genes, individuals in that population, but some of the individuals will get a better chance. We'll refer to that as differential reproduction. Combining heredity, genetic variation, and differential reproduction into algorithms can bring intelligent solutions from sheer randomness. Let's look at a crude example of how different operations of evolution work on different generations. So here we are looking at each level. There is one generation. We start with this, let's say, one individual in generation one. And in the next generation, that individual has some degree of variety. So the one of the offspring in the next generation is same as parent, but two are varying in color. In the third generation, we see that there is another operation that is selection operation. So beyond third generation, the process discontinued, passing genes of this particular individual. So we can say that unfavorable mutations are deselected from the process. In the fourth generation, again, we see reproduction and mutation is occurring, and due to that mutation, we see the variety that we had termed as genetic variation. In the generation 3, when we deselect this individual to pass on to the next generation, then what we are doing here is differential reproduction. In the fifth generation, we discontinue passing these individuals to the next generation, and only these individuals get a better chance to pass their genes to the next generation. And this process, if we keep on repeating for hundreds and thousands of times, biological evolution may occur maybe in hundreds of thousands of years, but in simulation, we can repeat this in seconds. And if we keep the same principles of heredity, genetic variation, and differential reproduction, we hope to see an optimal solution for a given problem. So the fundamental laws of evolution, well, we will refer to them as the survival of the fittest. So in a population in the environment, we have many generations in the left-hand side box. When they pass to the next generation, only few left. The others don't get a chance, or they didn't continue to the next. And in the third generation, rightmost box, we see some kind of variation coming through certain evolutionary processes, reproduction processes that we'll study. Now, if evolution brings some adaptability and better individuals or better generations over time, can we call it intelligent? If we accept that intelligence is the capacity of the system to adapt its behavior to ever-changing environment, then regardless of the form of the intelligence need not to look like humans. Intelligence, if defined to be adaptation, power of adaptation or becoming better over in many generations, then yes, evolutionary computation is intelligent. So if we can create computer-based problem-solving systems that work on these principles and solve problems that we come across in machine learning or other domains, then we can call them as intelligent solutions. So we are going to simulate this process. Result of the simulation is going to be a series of different steps and algorithms. Each step we are following some simple rules of to materialize evolutionary principles, and the only thing we want to study and encode in our programs is their repeatability. Over time, we repeat those processes and monitor the health of the solution with some kind of a function that gives us a degree of goodness of the next generation solution. And that's all. We can say that this proposition of bringing evolutionary principles in computations is quite well motivated. The only problem that we will be trying to figure out for a given solution, a given problem, the only thing we need to figure out is how we measure the goodness, how we measure the fitness, how we measure the appropriateness of the solution. So we need to have a yardstick for every problem. There should be a function in machine learning, you call it objective function or fitness function. So if the fitness function is good enough to measure and rank the individuals with respect to some criteria, then we are good. A chromosome, representation of a chromosome. We are going to learn today how to implement a genetic algorithm in Python. And the basic vocabulary we are going to revise. A chromosome is a set of genes that constitutes an individual, a solution. And consider this list of boxes as a chromosome that has around 10, 15 genes. There are some operations that if we do on the population of chromosomes, we expect that we one day will find the best possible solution. So anybody who want to remind me what is mutation? If we want to mutate this chromosome, mutation operation in genetic algorithms is going to do what? It's going to, let's say, change spaces. So this particular gene, we will take it from here and move its location from here to any other random location. Let's say we go there. And this one will move around here. If we replace that, so the red circle and black goes to red and red goes to black, we will say the chromosome or the solution is mutated. So given a list of things, if you just write a function that replaces their position randomly, take one gene and move it, swap its location with some other randomly selected gene. Let's say in here, if we have a dummy naive implementation of mutation, it will look like this. Can you see my screen, or shall I make the font size a little bigger? So here, the mutate function is doing this mutation operation. For every chromosome, we are going to call population. We are going to call them, let's say, roots. Every root has a root in it, so we want to mutate a root. In that case, what we say that let's generate a random number. A random number is going to output a number between 0 and 1, random function. And we say if that number is smaller than some threshold, mutation rate, let's say mutation rate is 0.1. So if we repeat this operation random.random 100 times, at least 10 times it will be smaller than this 0.1 threshold. So we can say that the probability of this if condition being true is 0.1, right? So it's kind of dummy implementation of probability, but in Python or programming, you can use random numbers to implement probabilistic events. So for every gene I, if the probability is less than given threshold, then you will generate another random number and multiply it with the number of chromosomes and number of genes in the chromosome. This J will represent what? It will represent the position for black circle, let's say. So we are right now at red, and red, the probability for changing red, getting red mutated, is falling within the threshold. So we now want to find which other gene we want to change it with. So we randomly select any other one, and let's say we get this black one. Black is the J. So we will just replace their positions. I will go to J, and J will go to I. And we do this for every chromosome in the population. The other operation we have is crossover. Special type of crossover we are going to use today is ordered crossover. Ordered crossover will do what? It is supposed to take a random part of your chromosome, any random part. Let's say we start from here and go up to this point randomly. So start and end point should be random, and we bring it down here. Actually, let's create two chromosomes. So chromosome A and B. And we are going to take this part from chromosome A, or solution A, and put it here. And then we are going to take from B the rest of the chromosome. But the only thing that we want to make sure here is that it's better if I color code them, right? So let's sprinkle some red, white, and blue. And let's do it again. We randomly take these 4 from A. They come here. And then the rest of the chromosome we take from rest of the genes we take from chromosome B, or solution B, to get a new solution or new chromosome. So from the image, you can see a crossover, general crossover, but how it becomes ordered, we need to take care of one thing. If when we are creating the child, the new solution, at that time, we want to make sure that when we add some point here, so this point is coming from chromosome B, this gene is coming from chromosome B, and it is not already one of the chromosomes that we took from A. So this is parent A, parent B. So if we take this from parent B solution, we take this particular gene and put it here. Before putting it here, we want to make sure that it is not already taken from A. Maybe, let's say, the value of this particular gene is A, something AA, and this one is also AA. In that case, before moving it to the child chromosome, we first want to make sure that AA is not already in the solution, included in the child. That's why it's called ordered. Okay, if it is already taken, then we are going to drop it, and we put this second gene over here. So whenever we, from parent B, when we take one gene and put it in the child, we make sure it's not already taken from A, and only then we include it in the corresponding position for the solution, child solution, and so on. So this, we can look at the implementation for crossover. If we have, let's say, these are the few lines that we are doing to achieve this. Given these two operations, mutate and crossover, what else is left that we need to take care of is selection. From a population, we need to select to implement survival of the fittest rule of a genetic algorithm. How do we do selection? We need to, there are multiple strategies, but today we are going to implement the elitist strategy. Elitist strategy gives ranks all the solutions with respect to some fitness function and take top n. So those top n solutions become the elites. They are guaranteed to have their genes passed on to the next generation. Selection function can be done like this. So if we have elite percentage parameter for the algorithm, let's say 10% of the population, we want to make sure that top 10% good chromosomes should pass their genes on to the next generation. So we can implement it by ranking the solutions and then finding the top 10. So this top 10 we take from here, from the list of solutions, and the rest of the solutions, 90% of the solutions, we just randomly select from them. In this line, we are doing that. Randomly select how many? As many as we have in the top 10. So top 10 is 10%, so same 10% we will take from the rest of the solutions, but randomly. Then what kind of problem we can solve with these three functions? Selection, mutation, ordered crossover, and mutation. If these three functions we can implement, then we repeat these three operations enough number of times, then we are guaranteed to find the best possible solution for a given problem. In the last session, we looked at a problem of finding the shortest path in a given territory. Let's simulate that problem here. Here we are doing a simple task of finding the shortest path. First, we randomly generate these red points. These red points, and consider them as cities. And we want to start from any given city and visit all other cities only once and come back to the starting point. So if there are 20 cities, then there will be how many possible routes? Too many to count. There will be so many permutations of city 1 to 20. You have 20 numbers. You can permutate them in a large number of possible solutions. How to find the best possible solution? By using a fitness function and repeating these three operations of genetic algorithm that we have here: selection, ordered crossover, and mutation. So let's first look at the first step is to generate. We don't need all possible solutions to run this algorithm. We can generate, let's say, enough number of solutions. So here we can randomly generate 100 100 roots. So when we are looking at finding the best root, we need to give as an input as the first generation some examples, and those examples need not to be the perfect examples, randomly generated. So this particular function is doing what? When we go here, we are, sorry, this find shortest root function, it's a prepare roots function, is doing randomly generating as many solutions as you specify. So in this particular example, we are specifying 100. 100 solutions are generated at time 0. Let's look at how these solutions look like in terms of Python list. So here you see the object city list, sorry, roots list. This is our population. So we randomly generated 100 roots or chromosomes. Every root has one gene. Gene corresponds to the coordinates of the city. First city has 457240 coordinates. Second city or gene has 204 and 493 coordinates. We have 100 chromosomes or possible solutions that we want to work on. So this particular function that we have here, it is just generating randomly a random arrangement of all the cities in a root and appending them to a list, roots list. So far, so good. What fitness function we can use to evaluate the goodness of a root? It's should be very simple, the distance, right? So there is a function calculate root length. It just takes distance from a city to another city in the list of cities. In every root we have 25 cities, and it adds their distance and returns root length. We are going to use this length of the root as fitness function. Once this population is generated, next we want to do what? We're going to apply the algorithm. After we rank these roots with respect to the length of the root, then the best root that we have here is the best root that we have here has this length, 3012, let's say, kilometers. All other roots are longer than this root, 3965. Third root is 4180, and the last root is 7500 kilometers. So the best root in our randomly generated population of possible solutions, roots, or chromosomes, the best solution on time 0 is giving us how much? 3012 kilometers. Now we are going to repeat these three operations that I explained in the beginning: selection, ordered crossover, and mutation. In the next generation operation function of this class, we are doing the same thing. So let's look at that. First, we rank the roots with respect to their length. Okay. So we go back to our line where we were. So if we look at selected roots, we see that we have 20 roots. Jasmika?
Yes, sir.
Can you see my screen?
Yes, sir.
So we have 20 roots from the first selection operation. Top 10 are because they are good, they are the best top 10, and 11 to 19 are randomly selected from the rest of the 90 solutions. Okay, so if you check 18th is giving 5,116 kilometers, the length of the route, but top 10 are like good ones. So here, even sorry, ninth one is 10th one. It is giving 4,751 kilometers. Top one is giving 3,000 kilometers. Does it make sense?
Yeah, you took ranked one and then you took random ones, right?
All right. The after selection, what next is this operation that we kind of made a schematic, ordered crossover. We do this ordered crossover, and from this operation, we are going to generate as many children as there are in the original population. But those children will come from this selected roots. Selected roots have half randomly selected, half selected based on their goodness. We will randomly choose, we will say, let's create a list of child roots. As long as child roots is length of child roots is less than the roots count or population that we have 100 population, we will repeat this operation. So we will randomly select two solutions or two roots or two chromosomes from selected roots, and we are going to use those two randomly selected solutions to produce a new root using this ordered crossover function. Ordered crossover is implemented in these 4-5 lines. We create a child root, we put none in every position, and then we randomly select 2 points, point 1 and point 2, to cut off the part from A. So like from here, A is from position A to position 4 to 5. So P1, we select P1 and P2 in here and cut that part off and put it in child root. And then in this while loop, we make sure that all other points coming from the parent B, root B, they go in the child if they are already not included in the child. That simple while loop is checking if city is not in the child root, then put the city or the gene on this position in child root. The outcome is a new child that we get from mixing two roots. The ordered crossover is doing what? It is creating as many new children from the selected roots as the population size. Our population size is 100. So ordered crossover will return us how many new solutions. Are you guys following? Or Yali?
Hello, Professor.
Hi. So child roots, how many shall we have here? If I open child roots here, we have 100. Why? Okay. Anybody else? Jasmika?
Yes, sir.
Why do we have 100 child roots as the output of ordered crossover function?
Because you loop through the 100, you just replaced certain chromosomes with another one, but the whole population is still 100.
So we do this operation of creating a new chromosome or new solution from two. So here two are, let's say, these parent 1 and parent 2 is producing the child. So we are mixing these two in ordered way in producing child, and we repeat this operation as many times as the size of the population. Okay. When I change the screen, you see my screen as well, right, Jasmika?
Yes.
All right, then child roots, we all agree there are going to be 100 child roots. They came from 20 child roots, 20 selected roots, but they are 100. Those child roots we are going to mutate now. If you remember what mutation is, we randomly choose a position and replace it with another randomly selected position in a root or in a chromosome. We randomly select a gene and replace it with another randomly selected gene. This is simplest form of mutation that we can implement, that we are focusing learning today. There are different variations of how to implement mutation operation, but if we get the basics, we can move on to the next one as well. So the mutation operation will return the mutated roots, and that is also probabilistic. Sometimes in mutate, if you remember, mutate is choosing this probability mutation rate. If not every chromosome or every solution will be mutated, if there is this condition is met, only in that case that chromosome will be mutated. And that's all. When we repeat these three steps, selection, ordered crossover, and mutate, as many times, here we are repeating it 500 times, then every time new generation that we prepare from these three operations is going to be better than the previous one, and we are bound to end up with the best possible solution. So I repeat this, move forward for 500 generations, and we get this particular output for this. Where is it stuck? Oh, wait a minute. So in this particular run, we started with on the x-axis we have generations. We ran this algorithm for 100 generations. We repeated these three steps. So we started with 5,000 kilometers. The best solution was 5,000 kilometers. And at the end, the solution that we have, the best solution, it has around 2,000 few kilometers. If we repeat this enough number of times, let's say 500 times instead of 100, then we are going to see now the best solution here is around 1,000 kilometers. That is really good. So we started with 5,000 kilometers best solution, and we ended up with this one, which is the best one. Now here you see a variable random state, if you change this, you will see that the solution and the problem both change. This random state parameter controls what random numbers you will see. In order to fix those random numbers across the solutions, you can fix this number. So 10, if you repeat this with 10 parameter, you will get the same solution, still randomly generated. So this is the best, this is the solution the algorithm found. And do you think this is the best path? Not yet, right? The shortest path will not be going back and forth like this, but it will be going across. So how can we optimize this? I'm going to put you to this task. There are 3 parameters: mutation rate, elite percentage, and the count of roots in the beginning, and number of generations. So these parameters you change and find out for which particular parameters we get a better solution than the one that we are getting right now. You can change the number of initial population from here. You can say I want to work with 250 and not 200, and I want to have not 25 but 30 cities in my solution. Mutation rate I want to keep as 0.005, not 0.01. And elite percentage I want to make it as 25% or 20%. So every change will have some impact on the final solution, and try to see which parameters make the final solution better, which parameter values make the final solution worse. Would you like to play with this code?